last lecture of the course.
Right. So thanks a lot to the organizers for the air conditioning, and I will. Should I close the door actually on that? Okay. So I will try to both follow and not. Well, I guess I will not follow John's tradition since this is the third lecture of the series. So I will try to make it more understandable. He said that the fourth one is the one that you shouldn't understand. So I will, since it was a long time since I last talked, I will begin with saying a few general things about automorphisms of Kähler manifolds. And I will, since people seem to be interested in seeing a proof of Gamos Theorem, which gives an upper bound on the entropy of an automorphism of a K3 surface, or of any Kähler manifold, I'll first do the proof of this general result, and then we'll talk about some specific structures for K3 surfaces. So first I need to remind you what topological entropy is. So let me recall that if you have XD a metric space, we'll be interested in epsilon separated sets. So an epsilon separated set. So epsilon, as usual, is some number bigger than 0 that's very small. So net epsilon separated set S inside X is a set S such that for any two elements in S which are not equal, the distance between them is at least epsilon. So that's an epsilon separated set. And of course, the empty set is epsilon separated, but you want to have an epsilon separated set which is as large as possible. So we're going to define curly S of X with a metric D and parameter epsilon to be the maximal cardinality of an epsilon separated set. So the largest number of epsilon separated points that we can fit into our set. So I'm not going to write the definition, but there's a kind of parallel, dual in some sense, notion where you can take an epsilon cover. So in other words, a set of points which such that they lie in your space, and any other point in the space is within epsilon of a selected point. And such an epsilon cover, instead of taking a maximal one, which could be arbitrarily large, you would like a minimal cardinality epsilon cover. So these notions are within some constant factors, they're the same thing. And now suppose that you have f from x to x, a continuous self-map of a metric space. Maybe you want to assume compact, although I guess for the definition it's not necessary, and maybe you want to assume also maybe separated or some countable basis. And the first thing is you define a metric, so a new metric, which involves now the dynamics. It's the supremum for I from 0 up to n of the distance from f to the I of x to f to the I of y. So we take 2 points and we follow them under the dynamics for time n, and we record the furthest they went apart. So a different way to say it is that so you do what I just said, but the quantity that you're interested in now is the following. So you define the epsilon approximation to V entropy to be the following: the limit as n goes to infinity of log. So now you use this metric to produce an epsilon separated set. So S x dn epsilon divided by n. So what are we interested in? Or maybe let me put a lim sup just to be on the safe side. So what are we saying? We're saying we're still looking at points in our space X, but now we're not interested in just epsilon separated points, but rather epsilon separated orbits. So we consider 2 points to be at distance epsilon if under time n they've gone away at distance epsilon or more under this iteration. So you are counting how many orbits, different orbits we can see if we watch our system for time n, but only if we consider two orbits to be the same if at some point they, if for all times they are within epsilon of each other. Okay, so this is what the entropy is if we are using this parameter epsilon, and h of f is defined to be the limit as epsilon goes to 0 of h of f epsilon. So this is the entropy, a very general definition. This is the topological entropy of this continuous map. And Gamos theorem is the following. So that if you have f from x to x, a holomorphic endomorphism of a Kähler manifold, so compact Kähler manifold, then the topological entropy of f is bounded from above by the logarithm of the spectral radius of f on the homology. So I remind you that this rho of f is the spectral radius of f of pullback of f acting on cohomology, let's say, on all the cohomology groups of x. So this is not the whole truth. A harder theorem due to Yonden is that if now you have any smooth map of a compact smooth manifold, so for any smooth map of a compact manifold, nothing to do with complex geometry, the reverse inequality also holds. Okay, so in particular, for Kähler manifolds, you know that there's an equality here. All right, so maybe let me just make one remark that so we can consider the following example. We can take gamma inside SL2C, a co-compact lattice. So you can construct such a lattice, for example, by taking a compact hyperbolic 3 manifold. And then you can consider the geodesic flow. So let me take f to be time 1 map of gt. Well, it's just, well, this matrix acting on the right for t equals 1. So the time 1 map of this map acting on gamma mod SL2C, acting on the right. So this is essentially the geodesic flow. And so what is the entropy of this map? Is it 0 or not 0? What do you guys know about the geodesic flow and negative curvature? It's not 0, right? So it has positive entropy. And what do you know about the action on cohomology for this map? What? So what's the action? I mean, what's the spectral radius? What is this number? How does the geodesic flow act on the homology or cohomology of? Sorry? Well, the map is homotopic to the identity, right? Because it's a flow. It's the time on map of a flow, so it is acting trivially on cohomology, right? So it means that this, rho of f is 1, so log is 0, and this is positive. So the conclusion is that this is not a Kähler manifold, right? So we need the Kähler assumption. And there are many other ways to see that this is never a Kähler manifold. Okay? Let's see. So the proof of Gamos theorem has two ingredients, but I need first a little bit of notation. So we fix a Kähler metric omega on X, and we'll consider the following map. So the notation is not standard, but I don't think there is standard notation for these objects. So we're going to embed X into n plus 1 copies of X, where little x goes to little x, and then f of x, and then up to f to the n of x. So we kind of keep track of the dynamics, and we call gamma of fn the graph, so the image of this map. So it's still x, but we've just embedded it in this very curly way inside the product with itself. And we can consider the following Kähler metric. So we use the fixed Kähler metric in each of these factors. So this gives us a metric. And as a metric space, this is just the product, L2 distance kind of product metric. But the key point is that, so I'll just make this as a remark, and I'm not going to be more precise on this, but the induced metric, so if dn is the induced metric on x to the n plus 1, for entropy, we can use, to compute the entropy using the formula that I gave there, it suffices to use the distance. So we can embed our space so we can use this metric instead of this metric d lower n, which I was using for the definition of entropy. So the difference between these two metrics is only linear. So there will be a comparison factor between them. You can estimate one in terms of the other, and there will be some linear factor in n. And when you take logs and divide by n, this factor just goes away. So it's really, there's no kind of harm in just working in this situation. So given this, we now, the proof will follow from two facts. So proposition 1 is that, so the volume with respect to omega n, with respect to this metric that we have there of gamma fn. So if we take this volume, take the log, and divide by n, this converges to the spectral radius of f in cohomology. And again, this is a fairly general fact, and the reason is that you can compute volume using just cohomology and not anything more complicated. So computing volumes for Kähler metrics is much easier than computing volumes for arbitrary Riemannian metrics. And the second proposition is that if you have V inside M, you have some complex manifolds. So this is a purely local statement, but it's the following. So you have a setup like this, and omega is a Kähler metric on M with bounded curvature, sort of sectional curvature. And then for any epsilon bigger than 0, there exists a delta bigger than 0. And delta depends on the following parameters. So let me say the bound on the curvature is some k. It depends on k and the dimension of v, and of course epsilon, such that the following holds. If we have little x inside v, then the volume of the ball of radius epsilon intersected with v is at least delta. Sorry, this is not 0, this is x. So what this is saying is that, so let me draw the picture of what's happening and what's not happening. So imagine that you have the three-sphere, the three-dimensional ball, and you could have two surfaces inside. So one could be like this, and it has some definite area. It passes, and you have a surface which passes through the origin, and has a definite area. But the bad thing that can happen is that you can have actually a surface which has boundary on the sphere, but which has very small area, but nevertheless contains the origin, right? So how can you see this? Well, here's the point, and you can just draw a picture that looks like this. So this is a surface which, again, lives in the 3-ball and has a very small volume, but it contains the origin. So we want to avoid this kind of picture. And this is a good picture, and this is not a good picture. And the claim is that when you're in the setting of complex manifolds, you always see at least something that looks more like this than like this. OK? So let me just explain first why the two propositions are enough. So well, the point is that we can apply the second proposition to the setup that we have over there, to gamma of fn inside x to the m plus 1. So the point is that the dimension of m here is growing, but the dimension of v is fixed. And so the dimension here is fixed, but this thing is getting larger and larger. And the proposition is telling us that for any point that we pick on this variety, if we take an epsilon neighborhood of that point, it has definite volume, right? So then this implies that the following inequality tells us that the volume of this gamma fn is greater than or equal to delta times the a maximal epsilon separated set of this guy for this guy. Right? So because so what is the picture? We have some kind of complicated gamma, and we know that whichever way we cover it in this epsilon separated fashion, each of the balls has some definite volume. It takes out a definite volume, and so this quantity is, since this epsilon ball is epsilon separated, you can control this quantity by the volume, the total volume of the variety, right? Because the balls are all disjoint. So now, if you just take logs and divide by n, and send epsilon and send n to infinity, you get the conclusion. Okay? So then we're done. So now for the proofs of the propositions, the first one, so for K3 surfaces, this proposition is relatively easy. So let me just try to write the. So I'll only give you a partial proof, so a sketch of a proof. So the volume of this gamma of fn is just the integral over x of omega plus f pullback of omega plus dot 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 plus f pullback to the n of omega to the power the dimension of x. So this is the metric that we defined, and so we have to integrate this volume form, but we know what we can do all the computations in cohomology, and for K3 surfaces at least, there's one. I mean, omega lives in H11, and once you have a hyperbolic automorphism, you can convince yourself that this quantity will grow at the right rate. Okay, so for general Kähler manifolds, there's a little bit more Hodge theory that has to go into convincing yourself that this quantity will grow at the maximal possible rate. Okay? A priori, it's not clear that for a Kähler form, you'll see this maximality in growth. Okay. Are there any questions? Yeah? Yes, on the for the manifold capital M, yes. Yeah, because you see, if I assumed bounded sectional curvature on V, this would be a lot easier. And in fact, I should say that this you don't need Kähler manifolds, and it suffices to assume that V is a minimal surface. So you have a weaker condition. In other words, it minimizes volume in its homology class. So you can convince yourself that this is not very minimal because you can push it that way. OK, so I will instead prove proposition 2 in a little bit more detail. But because I think also somehow the ideas that go into the proof of the proposition are very useful, and they involve a little bit of gymnastics with DD bar. And so you kind of get to see some of the ideas that appear in the subject. So the proposition follows from a kind of more general fact about complex manifolds. So I'll just make the following vague statement and say that because of the curvature bounds, it's enough to work in C to some power n. This is our ambient manifold, and omega is Euclidean, and x equals 0 is in V. So because of the fact that I'm assuming that my manifold has some bounded geometry at all scales, I can just assume that we're actually working in flat space. And since I'm not interested especially in the sharp delta here, this is safe. So in this case, we have something more general. So there's something called the Lungs inequality. And it says the following, that so we're in the same situation. We have 0 is in V inside C to the n, and V is properly embedded complex manifold. In fact, it doesn't even have to be a manifold. It can have some singularities for what we'll do. But what does it mean that it's properly embedded? It means that it doesn't just run off at some point. So of course, I could just say that this is my whole surface and take a much larger ball. So properly embedded means that yeah, the preimage of any compact set in Cn is compact in V. OK? So under these assumptions, the Long tells us that 1 over, so let me say that the dimension of V is equal to D, so the complex dimension. So then if we consider the volume of this manifold in the ball of radius r, so let me call it omega to the d. This is what the volume is. So this is a function of r. So the claim is that it is an increasing function of r. So of course, if I didn't put the division by r to the 2d, this would be quite clear, right? I'm taking the volume of something bigger and bigger. But the claim is that it is increasing even after you divide by this normalizing factor. So here's a question. What does this tend to when r goes to 0? So what happens when r goes to 0? So we have our manifold, looks something like this. And we take a big ball, but then we start shrinking the ball. The limit will be some universal constant, which is not 0, right? And so in particular, it implies that, so then let me say it like this. It's some constant which just depends on the dimension of the manifold. Some area, depending on your normalizations, you know, it's the volume of the d-dimensional sphere or some such thing. And more importantly, it says that you have a universal lower bound. So let me just write now the corollary. I just want to keep it here. So the corollary is that this integral, which is the volume that we're interested in, it grows with the radius at a uniform rate, which is independent of the manifold. Okay? Because the function is monotonic. And equality is achieved if V is flat. So the other remark I want to make about this inequality is that it's interesting both when R is small, but it's also interesting when R is huge. So if you have some manifold which is quite wild at infinity, it still tells you something about the behavior at infinity. OK. Are there any questions? Yes?
Can you repeat why the limit is not 0?
Well, you see, we're normalizing by R to the 2D. So when we take a very small ball, this manifold starts to look flat. And it's approximated by its tangent space. And then we're taking the volume of a ball of radius R, which is R to the 2D times some universal constant, approximately.
Okay.
And we're dividing by that. Yeah. So that's why it actually tends to a constant and not to 0. OK. So we've reduced everything to that proof. Oops. And the proof will involve two facts. And the facts are the following, that omega, the Kähler metric, we can write it as dd bar of z squared. So this is called the potential for the Kähler metric, meaning that if you take this Laplace-like operator, you obtain the flat Euclidean metric. And the other one is that if you consider now dd bar of log of z squared, then this thing is greater or equal to 0. So it's a positive current. I should say right away that I'll be a little bit negligent about what happens when z is equal to 0, which is why, in fact, one is allowed to have actually a finite limit. But this is a statement that everywhere away from 0 is to be interpreted by saying that this gives you, at each point, a quadratic form which is positive definite. OK, so it's a kind of like a Kähler metric. OK, and then we'll use Stokes theorem several times. So now there's just one way to do it, which is to compute. And we just compute. So let me, maybe before computing, let me just introduce some notation to make my life easier. We're going to call VR the intersection of the ball of radius r with V. And then we just have a computation. So we have to integrate the metric to the power d. And we'll take the first term and integrate by parts. This is 1 over r to the 2d minus 2. So OK, maybe in the interest of educational interests, I will do it in one step at a time. So it's integral over the boundary of r of minus 1 d bar z squared times. OK, so I'll just write here omega to the d minus 1, since that term doesn't bother us for a moment. And then we have, again, now here I'm going to take an r squared, and I'm going to put it in here. And the nice observation here is that what's d bar of z squared over z squared? That's the same as d bar of log z squared. So this is, so I'm going to, so let me just put as an aside what I said in words. So I said that d bar of z squared over z squared, this is the same as d bar of log z squared. And so now I trade two powers of r here to get d bar of log z squared, and then omega to the d minus 1. And now I integrate by parts again. Oops. and this is 1 over r to the 2d minus 2, the integral over now Vr of I dd bar log z squared, and then I dd bar of z squared to the power d minus 1. And I keep doing this d minus 1 more times to trade this z squared for log z squared. So after a long computation, you get that this is equal to the integral of a Vr of minus 1 dd bar log z squared to the power d. And now you're actually in good shape, because it's knowing that this quantity is positive, you're integrating as a function of r, you're integrating over a larger and larger set. So this quantity is visibly monotonically increasing in r. OK? So this is a slightly, it's an elementary argument, but it's also quite powerful and very special to complex geometry in the sense that we've used kind of positivity at several points in the argument. OK, other questions about this? No. All right. So I explained the proof of Gamos theorem to you. So now we're back to K3 surfaces. And automorphisms. So one thing that I mentioned in the first lecture, but it didn't come up later on, is that there's a big distinction between when a K3 surface is algebraic and when it is not. So let me remind you that we had the Néron-Severi group of X, which was this H11 intersected with H2 of XZ. And the fact is that X is algebraic, which for us means that there exists an embedding into some projective space. So this is equivalent to there exists some class gamma, let me call it L, inside the Néron-Severi group of X, such that L squared is a positive number. And so this is a condition for the K3 surface to be algebraic. If you're familiar with it, it's related to the Kodaira embedding theorem. One thing that I didn't say in the first lecture is that the Néron-Severi group of X is also the kind of recipient for the classes of the algebraic submanifolds inside X, in particular sub-Riemann surfaces. So if you need to have at least some kind of collection of submanifolds in there, and as soon as you have something that is positive in this appropriate sense, you can actually have many more of them, and you can embed your X into projective space. An important invariant kind of complementary to the Néron-Severi group of X is what's called the Transcendental Lattice. So T of X is defined to be the orthogonal complement of the Néron-Severi group of X. And so you can take this in the sense of lattices, so preserving the Z structure, but you can also complexify. And sorry?
On NS.
Oh, yeah, I'm sorry. Thank you. And you can complexify, and we'll do that in a moment. But the relevance of this discussion, the difference between algebraic and algebraic is the following proposition. So you have f from x to x. Sorry? In H2, in all of H2. So it's kind of the rest of the cohomology. OK, so if you have a holomorphic automorphism, then the first fact is that if you pull back the holomorphic one form, two-form. It's again a holomorphic two-form, and they're unique up to scale. And the scaling, so this scaling parameter has absolute value 1. And the second aspect is that if x is algebraic, then delta of f is a root of unity. So let me prove this fact, and then I'll explain the relevance to to dynamics. So proof. So the fact that the holomorphic two-form is proportional to the previous one is for the reason that I said, namely there's a unique one up to scale. So if you pull it back, you must have gotten back the same thing up to scale. And why is it absolute value 1? Well, the volume of x, the integral over x of omega wedge omega bar is equal to the integral over x of the pullback. And plugging things in, you get that the absolute value is 1. And for 2, we have to look a little bit at the transcendental lattice. So we have that H2 of x, let's say at least over a field, so let me say it with complex coefficients, decomposes as the Néron-Severi group of x with complex coefficients plus the transcendental lattice with complex coefficients. And we also have the Hodge decomposition. So on T of x with complex coefficients, we have H20 plus H1, so let me call it T11 plus H02. So to go back to your question, this is the complement in H11 of the Néron-Severi group, but the H20 and H02 are always there. Okay? And the signature of the inner product, here it's +1, here it is, well, so here it depends on what's happening in the Néron-Severi group. So if, let me just, as an aside, remember, what was the signature on H11? So for the inner product, the signature was which one? 119. So it was indefinite, and we had one positive direction and 19 negative directions. So if we're in the algebraic case, the assumption is that there's a positive direction in the Néron-Severi group. Okay? So here we have signature essentially 20 minus rho, where rho is usually denotes the rank of the Néron-Severi group of x. But it's important that it's negative definite. So I guess I want to say minus 20 minus rho. And here you have, again, signature +1. Oops. And now, if you stare at this picture, you notice that the holomorphic automorphism preserves this decomposition. And so it acts as an isometry for a metric for which, if I flip the sign on this factor, it actually acts as an isometry for a positive definite metric. And it's also integral. So f pullback is integral on T of x, and isometry for what people would call the Hodge metric. And if you have an integer matrix, which is an isometry, it's finite order. And so it has its eigenvalues are roots of unity. And it's clear from this expression that, remember, H20 was generated by omega. So this delta of f is just the eigenvalue of f pullback on this factor. So then you get that the eigenvalues are roots of 1. Are there any questions about the proof? So the reason why this affects the dynamics is the following. So I wanted to do this example in more detail, but I'll put it in the notes in more detail. So here I'll just say mostly in words what's happening. So you can have a fixed point of the dynamics which is elliptic. So near a fixed point of f, where not just near, but at a fixed point of f, can have df at, let's say, x, at a fixed point of x of f. We can have the derivative be conjugated to something like this, e to the I theta 1 and e to the I theta 2. And you could ask if such a dynamics is linearizable or not near such a fixed point. And a theorem of Siegel tells you that this is so, provided that theta 1 and theta 2 don't satisfy, well, first they have to be linearly independent, and they also have to satisfy a Diophantine condition of the type that appeared, for example, in Giovanni's talk. And you see that if you are a root of unity, if the action is by root of unity, so this means that the sum of these two phases is a rational number. Right? This is how it will act on the 2 form if you look at the pullback. And it means that in particular there's a linear relation between these angles. So if you are in the algebraic case, you have what people call in dynamics a resonance, meaning that there's some linear relation between these exponents. So you cannot have linearization. Or typically you do not expect to be able to linearize the map. However, what McMullen did is he constructed a non-algebraic K3 surface which has so he can arrange for not only are they linearly independent, but theta 1 and theta 2 are non-resonant and satisfy a Diophantine condition. So then you have a linearization. And once you have a linearization, you have a whole domain where f acts like this matrix. And when that happens, you know that there's some domain in which the dynamics is very simple and essentially acting by isometries. Okay, so I will not tell you so much about how he does it. Maybe just kind of as an aside, let me just say a few words about Salem numbers, because I think this is of interest to at least some people in the audience. So what is a Salem number? You have, say, lambda, a real number, which is not an integer. So this is an algebraic integer, is Salem if all conjugates, all Galois conjugates of it, if all the Galois conjugates of lambda, except for possibly lambda inverse, are on the unit circle. So what this means is that if you draw the, so here's 0, so you can have, say, here's lambda, here's lambda inverse, and then you have all the other roots which come in complex conjugate pairs, because this is a real algebraic number. Well, yeah, they will come in complex conjugate pairs. And so if what you know about these numbers is that, so if you, let's call S of t, right, Z of t, this is the minimal polynomial, then you'll have a symmetry, z to the 2d, t to the 2d times s of 1 over t is equal to s of t. So of course, 2d is the degree of s. So this implies in particular that s of t is t to the d times r of t plus 1 over t, where the degree of r is d. And for example, as we saw from Gamov's theorem, we have that log. So a consequence of Gamov's theorem plus the structure of K3 surfaces is that the entropy of an algebraic automorphism is a log of a Salem number. OK. So what McMullen does is he constructs certain Salem numbers which one can arrange to have this kind of property. And also, moreover, you need to also somehow ensure that you have a single fixed point for f. And that's also a little bit tricky because you want. Can you say again this was, how did you get this Salem number from the why is it log of a Salem number? Well, because essentially because of where is it? Here. Because of the structure of the second cohomology. So the signature on H11. The signature in H11 is 1, 19. And the automorphism on the eigenvalues that it can have on that factor, there's, well, you agree that the entropy is a log of an algebraic number. Do you agree with that or no?
According to the theorem, it's the spectral radius. Yes.
Yeah. So the spectral radius is essentially realized on the H11. And on the H11, you'll have one number. If it's positive, the spectral radius is bigger than 1. If it's bigger than 1, then there will be an eigenvalue bigger than 1, an eigenvalue less than 1, and all the other ones will be of absolute value 1. And similarly, on H20, the eigenvalues will be of absolute.
Two positive eigenvalues. And yesterday you explained to me that there is only one.
What do you mean positive?
Between lambda and lambda inverse.
I'm saying of absolute value bigger than 1. No, so one is of absolute value bigger than 1, and the other one is of absolute value less than 1.
But doesn't this mean you have two isotropic directions?
No. So you have you have the usual picture, e to the t and e to the minus t, and there's one isotropic direction at most.
Okay.
Okay. Good. Any other questions? Okay. So let me, in the remaining 10 minutes of the course, say a few things about the kind of more analytic properties of automorphisms of K3 surfaces. So let me just start like this. So theorem. So I will state the theorem first, and then in the remaining time, I'll try to explain some of the concepts and what they mean, and more importantly, how are they defined? Because when you see the statement, you might argue that some of the objects are not well defined. So the theorem due to Cantat is the following, that there exists, so f from x to x, a hyperbolic automorphism, where equivalently positive entropy, this is what I mean by hyperbolic, then there exist closed positive currents. So I'm going to use currents in the same sense as Giovanni was using, meaning they're generalized functions, but they're dual to forms, to differential forms. So there exist closed. I'll explain what positive means. Currents, we call them eta plus and minus, such that if you apply the dynamics to one of them, it scales by the eigenvalue. So lambda is, yes, rho of f. So this is the first fact. Moreover, these currents are, so as I said, they're closed and positive. these currents, eta plus and eta minus, are unique up to scale. So certainly if I have one such guy, I can rescale it by a real number, it will still satisfy this, but essentially otherwise they're unique. And have older potentials. So again, I have to explain, we'll explain to you what potentials are. So the potentials are objects which are only defined locally. However, once you have these Holder potentials, you can define, so as Giovanni emphasized, you cannot take the product of two currents in general. You cannot multiply the delta function at 0 with itself. But with certain better behaved currents, you can do that. And these currents, in fact, allow a process of multiplication. And what's true is that if you square them, you get 0. And if you define mu to be eta plus by eta minus, so you normalize it to a probability measure, then mu is the unique measure of maximal entropy. Moreover, it is also mixing, and so in particular, it's ergodic. So I did not define the entropy of a measure, but there is, in fact, a generalization of the concept of entropy that relates to, that depends on the measure and not just on a smooth map or a continuous map. And there are plenty of other measures on the K3 surface. In particular, there is Lebesgue measure. And it's certainly not known whether Lebesgue measure has positive entropy or not. Let me just make one remark about this measure mu. That you might ask, what is the relationship between the measure mu and Lebesgue measure? And the fact is that they're not usually very related. So Cantat and Dupont proved that, so if mu is absolutely continuous with respect to Lebesgue, and then what you can conclude is that this pair x and f is a Kummer example. So I haven't told you what a Kummer example for automorphisms is, but you know what a Kummer example is, at least for a K3 surface. You start with a torus, and you do this blow down and quotient construction. And if you have a linear automorphism of a torus, it can, if you're lucky, it will survive this construction of taking a quotient and blowing up. And this way, you'll get an automorphism of a K3 surface. But that's the only case in which you have some understanding of the relationship between Lebesgue measure and measure of maximal entropy. OK, other questions about this? Yeah?
Do I understand correctly that this cannot happen on algebraic K3?
What cannot happen?
Hyperbolic automorphism.
No, it can. I gave you an example last time.
But doesn't this, so then can you say again, so doesn't this say that it is algebraic and all eigenvalues have the roots of unity? And so
I didn't say all eigenvalues have to be roots of unity. Did I say that?
Because then you have positive. Anyway, it goes so fast that I'm sort of, maybe I hear things you didn't actually say.
It's possible, yeah.
I heard things you didn't actually say, so that's why I'm asking. So, okay.
No, I'm not claiming that all eigenvalues have roots, have absolute value. I mean, that.
You somehow preserve the positive, you preserve the NS, which is positive definite, you preserve the orthogonal.
I mean, there could be, you see, for example, in the Kummer case, the automorphism, the linear automorphism, will have a 16-dimensional space, which it doesn't touch at all, essentially. We're attacked by a finite permutation. You know, the cohomology of the 4-dimensional torus is quite small dimensional, and the automorphism is not doing much there. So this is absolutely compatible with having most of eigenvalues trivial, in fact, 1. Okay? So the algebraic degree of the Salem number is not necessarily 22. It could be any number less than 22. Okay. So let me, okay, maybe I'll end with just telling you what positive currents are, and with an exercise. And it's the following. So locally, so positive currents. So we have eta inside. I'm going to denote by d11 of x. The distributions which are dual to 1, 1 forms on x. X is a surface. So this is the same as to say that you can think of it as a 1, 1 form with distributional coefficients. So such a gadget is positive if for any alpha a 1, 0 form, smooth, you have that if you pair alpha with eta with this kind of manifestly positive guy, alpha wedge alpha bar should be something that's positive, you get back something that's positive. So this is the abstract definition. One remark is that when you work on higher dimensional Kähler manifolds, there are several different notions of positivity. However, for surfaces, they're all the same. And the exercise is the following. The exercise is that if you have in local coordinates, if eta is equal to an expression like this, some eta I j bar, dzi, dzj bar, where eta I j bar now are generalized functions, so they're duals to, they're just distributions, then eta is positive. So this is what I mean by positive. This is how it's denoted. Implies that eta I j bar are locally finite measures. So they're not some kind of wild generalized functions, but in fact their measures may be signed. Okay? And so this already imposes some regularity on positive currents. And in particular, it implies that appropriate spaces of positive currents, once you bound the total mass, they can have compactness properties that they inherit from the spaces of measures. Okay? And the last maybe remark that I want to make is, how do you define the product of a current with itself if it has some positivity properties? So this is called Bedford-Taylor theory. So a potential locally, so if you work in a chart, a potential is just a function which satisfies dd bar of phi is equal to eta. So this is locally. In each chart, if you can find such a function, you call it a potential for eta. And if you have now two such things, phi I is equal to eta I, and assume that we have to assume two things, that eta I are both positive, eta 1 and eta 2. And for simplicity, I'll assume that phi I are continuous. What you can do is you can define eta 1 wedge eta 2 as I dd bar of phi 1 wedge times eta 2. So I dd bar will kill this term, and it will just give you here eta 1. Now, the thing to notice is that this is a distribution with measure coefficients, and this is a continuous function. So you can actually define, this is a well-defined distribution, and you take this object in the sense of distributions, which you're allowed to. You're allowed to differentiate. You're not allowed to take products, but you can differentiate as much as you want. And this is a definition, but it's not even clear that it's commutative, right? If I exchange the two, the order, I'm supposed to get the same result, but the definition is different. Nevertheless, what the basics of the theory tell you that this is well defined. It is commutative, and in fact also you'll have that eta 1 by eta 2 is itself bigger than or equal to 0. And it gives you a measure whose mass you can compute, again, using homological constructions. OK, so I have at least sketched the definition of most of the objects in the theorem. I should say that the proofs are not too difficult, assuming that a lot of this machinery of pluripotential theory is set up. But there are still many questions, in particular related to Lebesgue measure and how to understand that. So I will, in the lecture notes, I'll put some references. And I should say that I think one of the best references, not for the dynamics of K3 surfaces, but just for the geometry of K3 surfaces, is there's an asterisk volume with lecture notes by various French mathematicians. So if you read French, it's a very good place to learn about K3 surfaces. But I'll end the course here. Thank you.